Kia ora, hi, it's me, your teacher. I am just making a couple of videos on solubility, Le Chatelier's principle, and writing KS expressions or solubility constant expressions from dissolution reactions. Those are all big words. We'll just get stuck in with saturation. So if you're in my class, you have done a little tiny bit on saturation and solubility already. We did a lab on it. But the main things to remember about saturation is that this is when there is no more room in the solvent. So remember, solvent is the liquid that things are dissolving into, for more solid to dissolve. So when a solution has become saturated, that's where you have your beaker with your water in it or your solvent. You're adding some of that's supposed to be solid, I don't know what it's ended up with, some solid to the water, and you're mixing it to dissolve until there is a point where no more of that solid will dissolve, no matter how much you stir or heat it, because that liquid has become saturated. There is no more room in that solvent for any more of that solid to dissolve, and we call that saturation. Solubility is a really important part of this because different amounts of different substances will be needed to reach that saturation point. So for example, if I have substance X, and substance X has a solubility of 2.3 grams per litre. So what that means is that I can dissolve up to 2.3 grams of substance X in 1 litre of water before it will stop dissolving. So once I have reached that 2.3 gram limit, say that I add 2.4, 2.6, 5 grams of substance X, anything over that 2.3 grams will not dissolve. It's just going to stay in the bottom of the beaker and refuse to dissolve. But substance Y might have a solubility of 50 grams per litre. So that means that for substance Y, I can add up to 50 grams of that substance, and that 50 grams will dissolve fine, and any more than that is going to sit at the bottom of my beaker. So that means that obviously I can dissolve lots more of substance Y than I can of substance X, which means that substance Y is more soluble. So it dissolves more easily and more of it will dissolve. We call substances that have a very low solubility, so 2.3 grams per litre is actually pretty high. You can get substances that will only barely dissolve. Tiny, tiny amounts of the solid that you add will dissolve in the water. And we call these things sparingly soluble. Oh my god, stop. Sparingly soluble. So when something will only kind of dissolve a little tiny bit, we call that sparingly soluble, or a sparingly soluble salt or solid. This is important because you can have reactions that will form a precipitate. So say for example, I'm going to make up a whole bunch of numbers now. So X plus Y gives us Z and Q. Really good alphabet there. Let's say, again, like we've got up here, we have 2.3 grams per litre of X. We have a solubility of 50 grams per litre for Y. Let's say that Z has got a solubility of 10 grams per litre, and that Q has a solubility of, I'm going to make this not a equilibrium reaction just for reasons, and Q has a solubility of 0.003 grams per litre. So you can already see that Q is far less soluble. It is more insoluble than any of the other things that are present in this reaction. So let's say that I dissolve 2 grams of both of these things. It's obviously going to be different numbers of moles, so don't at me, we're just going to pretend that this is all fine even though it isn't. And we're going to make, say, 5 grams of this and 1 gram of this. Again, this doesn't make any sense. Pretend that it does, but it doesn't. What this will mean is that my X and Y have both dissolved because I have attempted to dissolve an amount of a mass of each of those things that is below their solubility level. So I can happily dissolve 2 grams of X and 2 grams of Y. Both of those will dissolve, no solid will be left over. Those two things will then react in the water and produce Z. And Z can, we're going to produce 5 grams of Z because I've decided, and not for any other reason. We're going to produce 5 grams of Z, and Z has got a solubility of 10 grams per litre, which means that up to 10 grams of Z can exist in that water before it's going to come, before it will stop dissolving, which means that that's fine. I've got 5 grams in there. That's totally all right. That's beneath its solubility level. We're all good. However, Q is insoluble. It has got a very low solubility of 0.003 grams per litre, and I have made 1 gram of it, I've decided. Not really, but we'll pretend. I've made 1 gram of it. That's too much. What this will do is that even though what I've added were these two things, X and Y, those two solids, I've dissolved them and they have made 2 new products, Z and Q. Z is going to stay in that water because it's below its solubility level. There's lots of room for 5 grams of Z in that water, but that Q, there is not enough room for that much Q. So what we're going to get is a precipitation. Q is going to come out of the solution as a solid. So a solid is going to form. It's really easy to assume that a precipitation is actually just leftover solid from the start. But if we think about our solubilities here, it can't be leftover solid from the start because all of that stuff should have dissolved based on its solubilities. So instead, we have made a new product, and that new product has precipitated or come out of solution. Precipitated or come out of solution. This is kind of cool because you're making a solid out of liquid. It's kind of a weird thing to think about, that solid is actually sitting in the water, in your solvent, and it's been made by your reaction. You've produced this. It was never there to start off with, which is kind of cool. Because reactions will happen quite quickly, sometimes it's hard to visualize this, but it is what's happening. You're making a solid, and that solid is something that you didn't start with, which is kind of cool. When we have these sparingly soluble reactions, these sparingly soluble salts that we then dissolve in water, and we're really only going to think about water in this case because our topic is aqueous chemistry, so chemistry that's going on in water. So say we've got something like lead chloride. So lead chloride is fairly insoluble. It is sparingly soluble. Only a small amount of lead chloride will dissolve in water. And it will produce its ions because it's an ionic substance. Ionic. It produces its 2 ions, lead and chloride. You guys have got your table of ions at home, hopefully with you. But remember, we want to be kind of attempting to come up with methods to be able to get those just from your normal periodic table because you won't have your table of ions in your exam. So lead may be one of the ones you have to just remember. But you can also work it out from your chlorine. So your chlorine, you can see you've got 2 of them. Each chlorine is in group 7, which means that it has a charge of -1. So if I need to have 2 Cl minuses to match up with my lead, that means that my lead must be 2+ because we want our charges to cancel out. So now this is a +2 plus -1 times 2 gives me 0. So that's a happy balanced equation. This is in equilibrium. So even though we would look at this beaker, this test tube where we've dissolved a tiny bit of lead chloride and the rest of what we've added is just sitting at the bottom, it will look like nothing is happening. As with most equilibrium reactions, once it's reached equilibrium, it looks like it has finished, in air quotes. It's not doing anything. But we know that because it's in a dynamic equilibrium, what is actually happening is that the forwards and backwards reactions are happening at the same time, which means that as more lead chloride dissolves, some of that, the lead ions and the chloride ions that are in our solution are coming back out as solid. So as lead chloride dissolves, lead and chloride ions come together to form solid lead chloride. So we put our state symbols in there. You start with your solid lead chloride and we're forming aqueous ions of lead and chlorine. In the next video, I'm going to go on to some more of these dissolution equations. This is called a dissolution equation, or a solid dissolving in water to form ions. We need to be fairly comfortable with writing these, as this is kind of an achieved level point in your exam. But you have a lot of practice in writing them, so don't stress too much. So sparingly soluble precipitation reactions based on saturation and solubility. Like and subscribe, etc. Kia ora.